When IPv4 was introduced, the concept of classes were part of the overall strategy. Class A, Class B, Class C. Class A was designed for large networks. Class B was designed for medium-sized networks. And Class C was designed for smaller networks. So, for example, the large organizations in the world were handed out a Class A address. Fair enough. Medium-sized organizations were handed out Class B addresses. Good. Small organizations, Class C. It was as simple as that until networks exploded in size. And once networks exploded in size, well, the realization of extreme wastefulness was brought to the forefront. You see, Class A, B, and C. Large, medium, small. Large, 16 million devices in a single local area network. 65,000 devices in a single local area network. 254 devices in a single local area network. Only one of these makes sense. That's right. Only one of these makes sense, and that's the 254. We typically do not want more than 254 nodes inside of a LAN. Why is that? Broadcast communication. When we have everybody broadcasting at the same time, that would create 254 devices broadcasting. That's a lot. All right. Then would it make sense to have 65,000 devices broadcasting in a local area network at the same time? No. What about 16 million? Think about the amount of competition for network resources if there were 16 million devices in a single local area network. Now, I'm not saying 60 million in your whole organization. That's not what I'm saying. I'm saying in a single local area network off a single router interface. That's what I'm referring to here. Because in the original deployment of Class A, B, and C, Class A, there you go. Deploy it off the router interface. Now everybody lives there. That was the original design, the original implementation. Wow. That's a lot of devices. It's a lot of broadcasting. It's a lot of problems and issues. So eventually it was realized this is not going to work because theoretically most organizations could get about 1,000 devices or more, depending, right? But it depends on the time. All of a sudden, video and audio and everything was high bandwidth applications and resources were now being used. Well, yeah, you can't get away with 16 million devices in a high bandwidth network. So today's day and age, we only want maximum of 254 devices, which means we're only going to use Class C? No, of course not. We're going to rely on subnetting. How can we take a Class A network that could support 16 million and break it up into 65,000 different networks instead of one Class A? Now we have 65,000 of them, and each supporting only 254 end stations. So that's the concept of subnetting. Of course, a topic for discussion a little later on. We also have multicast addressing, Class D, which is heavily utilized for efficient distribution of video streams. So, for example, there is an on-demand, not an on-demand video service, but your television network is going to be sending out a stream for a particular movie or a particular sporting event that's on. Well, are we going to broadcast that to absolutely everybody? No, because that means the whole world gets it sent to their device, but only if they're on the channel does it make sense for them to get it. Whereas multicast, you go to the channel, and the channel, then your set-top box, then communicates back to the streaming service that says, hey, I need this. So all the routers and switches make sure that you eventually get that stream, and then it's displayed on your television. So the stream only goes to you if you request it. That's what multicast is all about. And then we have reserved Class C, which is not used today, used for experimental purposes. At one point in time, hackers were using it for malicious purposes and reasons, but if you try to implement even a Class E address on your device will not let you do that. Same thing with Class D. Class D is only for destination addressing. It's not for source addressing, meaning that you can't assign Class D addresses to end stations either.